Welcome to reneenergy.com, your renewable energy and sustainability platform. Welcome to today's exciting exploration into the world of hydrogen energy. Have you ever wondered how this simple element could revolutionize the way we power our lives? From powering vehicles to industrial applications and renewable energy production, hydrogen is carving out a significant role in our sustainable future. But what makes hydrogen so special, and what are the challenges in harnessing its full potential? In this video, we'll take a journey through the history, current innovations, and future prospects of hydrogen energy. Buckle up and let's dive into the fascinating world of hydrogen. Background of internal combustion engines. The internal combustion engine, ICE, is a heat engine in which the combustion of a fuel occurs with an oxidizer, usually air, in a combustion chamber. Invented in the early 19th century, ICEs have become the primary power source for transportation, including cars, trucks, and motorcycles. Various fuels have been used in these engines, such as gasoline, diesel, and natural gas, each with its unique properties and applications. The role of hydrogen in energy. Hydrogen is the simplest and most abundant element in the universe. It has the potential to play a significant role in the energy sector, especially in the context of reducing carbon emissions. As a fuel, hydrogen can be used in fuel cells to produce electricity or burned directly in internal combustion engines. It is considered a clean fuel because its only byproduct when combusted with oxygen is water. The utilization of hydrogen as an energy carrier has been explored in various applications, from transportation to power generation. Objectives and scope. This video aims to explore the historical development, current state, and future prospects of hydrogen-powered internal combustion engines. We will examine the early experiments with hydrogen as a fuel, the evolution of internal combustion engine technology, the environmental implications, and the ongoing challenges and opportunities in this field. By understanding the intersection of hydrogen energy with traditional engine technology, we can gain insights into potential paths towards a more sustainable and clean energy future. The scope of this video includes not only the technical aspects of hydrogen-powered engines but also the social, economic, and regulatory factors that influence their adoption and implementation. By considering these various dimensions, we can provide a comprehensive view of the subject and its relevance to the broader energy landscape. Early experiments with hydrogen as fuel. François-Isaac de Rivaz engine. François-Isaac de Rivaz, a Swiss inventor, constructed one of the first known hydrogen-powered engines in 1807. His experimental engine used a mixture of hydrogen and oxygen to create an explosion inside a cylinder, driving a piston and producing mechanical work. While the de Rivaz engine was a groundbreaking concept, it was more of an experimental prototype and never became a practical means of transportation. Other early prototypes. Following de Rivaz's work, several other inventors and engineers experimented with hydrogen as a fuel. These early prototypes laid the groundwork for future developments in internal combustion engine technology. For example, some researchers experimented with hydrogen-powered gas engines in the 19th century, while others looked at blending hydrogen with other fuels. Though these early attempts were essential in understanding the combustion characteristics of hydrogen, they were often hampered by technological limitations of the time. Challenges and limitations. The early experiments with hydrogen as a fuel faced various challenges and limitations. One significant challenge was the storage and handling of hydrogen, a highly flammable and low-density gas. The technology for compressing and storing hydrogen safely was in its infancy, making practical applications challenging. Additionally, the engines themselves were often inefficient, and the ignition of hydrogen presented difficulties due to its wide flammability range and low ignition energy. These technical challenges, coupled with the lack of a robust hydrogen infrastructure, contributed to the slow development of hydrogen as a viable fuel for internal combustion engines during the early stages of its exploration. Development of internal combustion engines. Gasoline engines. Gasoline engines, also known as petrol engines, have been the dominant type of internal combustion engines in passenger vehicles for over a century. Developed in the late 19th century by inventors like Nicolas Otto and Carl Benz, these engines use spark ignition to combust a mixture of air and gasoline. The resulting explosion drives a piston, which turns a crankshaft, thus converting chemical energy into mechanical energy. Gasoline engines are known for their relatively high power-to-weight ratio and have been continually refined to improve efficiency, emissions, and performance. Diesel engines. Diesel engines, named after their inventor Rudolf Diesel, were introduced in the late 19th century. Unlike gasoline engines, diesel engines use compression ignition, where air is compressed to a high temperature and pressure, and then diesel fuel is injected and ignites spontaneously. Diesel engines are typically more fuel efficient than gasoline engines and produce more torque, making them a popular choice for heavy-duty vehicles like trucks and buses. However, they tend to emit more nitrogen oxides and particulates, which have led to stringent emissions regulations. Comparison with hydrogen engines. Hydrogen engines represent a different approach to internal combustion, offering some unique advantages and challenges compared to gasoline and diesel engines. Like gasoline engines, hydrogen engines typically use spark ignition, but they burn hydrogen gas instead of gasoline. Efficiency. Hydrogen has a higher energy content by weight compared to gasoline and diesel, but its lower density can reduce overall efficiency. Emissions. Hydrogen engines emit only water and heat when combusted with oxygen, making them more environmentally friendly. However, the production and storage of hydrogen can have environmental impacts. Performance. While hydrogen engines can provide similar performance to traditional ICEs, they require specific design considerations due to hydrogen's unique combustion characteristics. Infrastructure. One of the major challenges for hydrogen engines is the lack of refueling infrastructure compared to well-established networks for gasoline and diesel. Modern hydrogen technology. Hydrogen fuel cells. Hydrogen fuel cells represent a significant advancement in modern hydrogen technology. A fuel cell is an electrochemical device that converts the chemical energy of hydrogen and oxygen directly into electricity and water, without combustion. In a typical proton exchange membrane (PEM) fuel cell, hydrogen gas is split into protons and electrons, and the electrons create an electrical current as they flow through an external circuit. Fuel cells offer high efficiency and produce zero harmful emissions, making them a promising technology for transportation, stationary power generation, and more. Hydrogen combustion engines. While hydrogen fuel cells bypass combustion altogether, hydrogen combustion engines directly burn hydrogen gas in a manner similar to traditional internal combustion engines. Modern hydrogen combustion engines have benefited from advancements in materials, ignition systems, and engine design, allowing for more efficient and clean combustion of hydrogen. They offer a way to leverage existing internal combustion engine technology while reducing harmful emissions. Research and development in this area continue, aiming to overcome challenges related to efficiency, reliability, and cost. Infrastructure and refueling. The widespread adoption of hydrogen as a fuel, whether in fuel cells or combustion engines, requires a robust infrastructure for production, distribution, and refueling. This includes facilities for producing hydrogen, through methods like electrolysis or steam methane reforming, pipelines or transport methods for distributing it, and refueling stations where vehicles can fill up with compressed or liquefied hydrogen gas. The development of infrastructure is a significant challenge and entails considerable investment and coordination between governments, industry, and other stakeholders. Some regions have made strides in building hydrogen infrastructure, while others are still in the early stages. Environmental impact and sustainability. Emissions and air quality. One of the key advantages of hydrogen as a fuel, particularly in transportation, is its potential to reduce harmful emissions that contribute to air pollution and climate change. When combusted, hydrogen only emits water vapor and heat, producing no carbon dioxide, sulfur oxides, or other pollutants that are common with fossil fuels. However, the environmental benefits are closely linked to how the hydrogen is produced. If produced using fossil fuels, there can still be significant greenhouse gas emissions associated with its production. Therefore, the full environmental impact must be considered across the entire hydrogen production and utilization life cycle. Renewable hydrogen production. The potential for producing hydrogen using renewable energy sources, such as wind, solar, and hydroelectric power, adds to its appeal as a sustainable energy carrier. Renewable hydrogen production often involves electrolysis, where water is split into hydrogen and oxygen using electricity generated from renewable sources. This method can be virtually emission-free, aligning with global efforts to transition to cleaner energy systems. Scaling up renewable hydrogen production requires advancements in technology, reductions in costs, and supportive policies and incentives to foster growth and integration with existing energy infrastructure. Economic considerations. The economic viability of hydrogen as a fuel is another essential factor in its sustainability. Currently, hydrogen production, particularly from renewable sources, can be more expensive than conventional fuels. Additionally, investments in infrastructure, such as refueling stations and distribution networks, add to the costs. However, ongoing research and development, economies of scale, and supportive regulatory frameworks can drive down costs over time. Analyzing the broader economic impacts, including potential job creation and industrial growth, can provide a more comprehensive understanding of hydrogen's role in a sustainable energy future. Case studies. Specific hydrogen-powered vehicles. Hydrogen-powered vehicles are at the forefront of the movement toward cleaner transportation. Several major automotive manufacturers have developed and released hydrogen fuel cell vehicles, FCVs, which combine hydrogen and oxygen to produce electricity and drive the vehicle's electric motor. Notable examples include the Toyota Mirai, Hyundai Nexo, and Honda Clarity. These vehicles offer similar driving ranges and refueling times to traditional gasoline vehicles while emitting only water vapor. They illustrate the commercial viability of hydrogen technology and its potential to revolutionize the automotive industry. Experimental prototypes. In addition to production vehicles, there have been numerous experimental prototypes that explore innovative ways to use hydrogen as a fuel. These include race cars powered solely by hydrogen, hybrid systems that combine hydrogen fuel cells with batteries, and unique vehicle designs tailored to hydrogen's specific properties. Universities, research institutions, and independent inventors often drive these experimental efforts, aiming to push the boundaries of hydrogen technology and find new applications and efficiencies. Industrial applications. Beyond transportation, hydrogen has found a place in various industrial applications. For example, hydrogen is used in high-temperature furnaces for metal processing, as a coolant in power generation, and as a feedstock in the production of chemicals like ammonia and methanol. Some industries have also begun to experiment with hydrogen as an alternative to natural gas for heating and energy. These applications demonstrate the versatility of hydrogen as an energy carrier and its potential to contribute to sustainability and emission reduction across various sectors. These case studies showcase the diverse applications of hydrogen in modern technology, from vehicles on the road to innovative prototypes and industrial processes. They provide real-world examples of how hydrogen can be harnessed as a clean, versatile energy source, offering insights into both current practices and future possibilities. Whether in well-established applications or cutting-edge experiments, these examples illustrate the tangible impact of hydrogen on the journey toward a more sustainable and environmentally responsible world. Future prospects and challenges. Technological innovations. The future of hydrogen as an energy carrier is strongly tied to technological advancements. Innovations in hydrogen production, storage, distribution, and utilization can drive down costs, improve efficiency, and make hydrogen more accessible. Research and development in areas like catalysts, membranes, and materials science are essential to unlock hydrogen's full potential. Collaboration between academia, industry, and governments can foster the necessary innovation and accelerate the transition to a hydrogen-based energy system. Policy and regulations. Governments and regulatory bodies play a crucial role in shaping the future of hydrogen. Policies that incentivize hydrogen production from renewable sources, support infrastructure development, and promote the adoption of hydrogen technologies can create a favorable environment for growth. Conversely, regulatory barriers or a lack of clear direction can hinder progress. Coordination at national and international levels is needed to align policies with global sustainability goals and to harmonize standards and regulations across regions. Public perception and adoption. Public perception and consumer acceptance of hydrogen technologies can also influence their success. Education and awareness campaigns that address misconceptions, highlight benefits, and showcase successful applications can foster trust and interest in hydrogen. Collaboration with stakeholders, including end users, communities, and non-governmental organizations, can facilitate dialogue and build support for hydrogen initiatives. Addressing safety concerns and demonstrating the tangible advantages of hydrogen will be vital in driving its wider adoption. Conclusion. Summary of key findings. This exploration of hydrogen technology, from its early experiments to modern applications and future prospects, reveals a dynamic and promising field. Hydrogen's unique properties, its potential to reduce emissions, and its adaptability to various applications make it a compelling energy carrier. However, the journey towards fully realizing its potential is complex, involving technological, economic, regulatory, and social dimensions. Implications and recommendations. The future of hydrogen is not without challenges, but the opportunities are significant. Continued investment in research and development, supportive policies, coordinated efforts, and public engagement are essential to harness hydrogen's potential. Collaborative actions across sectors, regions, and disciplines can foster innovation, reduce barriers, and promote a responsible transition to a hydrogen-based energy system. Emphasizing sustainability and aligning with broader environmental goals will be key in making hydrogen a cornerstone of a clean and resilient energy future. We've come a long way in our exploration of hydrogen energy, uncovering its unique properties, diverse applications, and the exciting opportunities it holds for a cleaner and more sustainable future. But as we've seen, the road ahead is not without challenges. From technological innovation to policy support and public perception, there are many pieces to the puzzle. However, with continued research, collaboration, and a focus on sustainability, hydrogen could very well become a cornerstone of our global energy system. If you enjoyed this deep dive into hydrogen energy and want to keep up with the latest developments, don't forget to like, subscribe, and share this video. Together, we can be part of the energy revolution. Thanks for watching, and see you in the next video. Thank you for choosing reneenergy.com as your go-to source for all things renewable energy and sustainability. With our YouTube channel, we explore the latest developments and innovations in the field, including hydrogen fuel cells and the use of AI and machine learning to optimize energy consumption. If you're ready to take the next step towards a cleaner, more sustainable future, visit us at reneenergy.com and discover the many ways we can help you transition to renewable energy. Thank you for watching and subscribing. Stay up to date on all the latest news and insights by subscribing today.